So the topic of discussion of today is direct memory access. In the short form, it is called as DMA, and it is also known as DMA data transfer scheme. And to help to do this DMA data transfer scheme, we have a controller, which is called DMA controller. It is available in two versions, 8257 and 8237. But before we go forward, that how this controller used to work, let us discuss about the DMA data transfer. Normally, the data transfer from memory to the input output devices or the input output devices to the memory, it can be achieved only through the processor. Now, when the data has to be transferred from memory to input output device, first the processor sends the address as well as the control signal to the memory to read the data from the memory. And then the processor sends the address as well as the control signal to the input output device to write the data to the input output device. Meaning thereby, whenever the microprocessor wants to transfer the data from memory to input output, first of all, it sends the address as well as control signal to the memory to read the information, put it in with itself, and then transfer. Then only it will be transferring to the input output devices. Similarly, when the data has to be transferred from the input output device to the memory, first the processor sends the address as well as the control signal to read the information from the input output devices. And then once it is able to read it, then the processor is going to send the address of the memory where it has to write, as well as the control signals of the memory device to write the data on the memory. So it means whenever in between two devices, the data has to be transferred, microprocessor comes into the picture. And so this is going to take a lot of time, because if it is possible to transfer the data in between the devices without any intervention of the microprocessor, then it will be a good way of transferring the data. So if we want to transfer the data directly between the microprocessor, between the memory and as well as the input output devices, however, they are connected with the common bus, but processor has to come into the picture, because every time it is going to select the sender device, means the source device, read the information, and then transfers it to the destination device. So, and if we have to transfer bulk data from one place to another place, this process become very slow. So a scheme has been developed known as direct memory access, or the DMA scheme has been developed, in which the input output devices can access the memory directly for the data transfer purpose, or even though in between two memory, the data can be transferred directly. So this DMA data transfer scheme is useful to transfer large amount of the data between the memory to memory, or in between the memory and the input output device. So for that, this direct data transfer between input output device and the memory, we are in requirement of a dedicated hardware device, which is called as DMA controller. And this DMA controller temporarily borrows the address bus, data bus, as well as the control bus from the microprocessor, and then transfers the data byte directly from the input output port to the series of the memory location, or from the memory location to the input output ports. Even there are DMA controllers which can also perform the transfer of the data in between the different memories also. So it means this direct memory access data transfer scheme is a scheme in which the high speed data transfer used to take place. Now, if you talk about the other data transfer schemes such as status check input output or interrupt based input output, the data transfer is relatively slow because each instruction need to be fetched and to be executed. In DMA, the microprocessor unit releases the control bus to the device which is called as DMA controller, and this controller manages the data transfer between memory and the peripheral under its control and going to bypass the microprocessor unit. So conceptually, this is an important input output technique, and it is going to introduce two different signals, two new signals which are available in 8085. These two signals which are helpful in doing the DMA data transfer scheme is known as hold signal and the HLDA signal. Now, what is the purpose of hold signal and HLDA signal? A hold signal is a high active signal and HLDA signal is a low acknowledged signal. Now, what is the hold signal? Hold signal is an active high input signal to the microprocessor 8085 from another master requesting from another input output device or the controller requesting the use of the address and the data bus. And after receiving the hold request, the microprocessor unit releases, relinquishes, leaves the control on the buses in the next machine cycle. Whatever it is doing, it will complete its operation and then going to relinquishes the control of the buses. And all the buses are now tri-stated, as well as the hold acknowledge signal is being generated and sent out to that device which has made a request through the hold signal. And so whenever hold signal is high, it means the microprocessor has to release its address bus, data bus, and control bus to the requesting device. And if the requesting device is a DMA controller, so it means these buses will come under the control of the DMA controller for actual data transfer. And whenever the work is over, means the data transfer is over, the controller will send a low signal onto the hold line so that microprocessor will be able to know that the operation is over. Now it resumes its work. So, and what is HLDA signal? HLDA signal is a hold acknowledge signal. This is also an active high output signal, which is indicating that microprocessor unit has relinquishes its control on the buses and allowed the DMA controller to take care of the buses, use those buses for the actual data transfer. Now, this DMA controller uses these two signals, hold signal and the HLDA signal. If it were a peripheral is going to request the microprocessor for the control of the buses. And microprocessor units communicates with this DMA controller by using three lines. One is chip select line, buses, as well as the control signal. However, once the controller has gained the control, it is going to play the role of a processor for the data transfer operation. And to perform the functionality of DMA controller, to perform the function of DMA, that is direct memory access transfer, the DMA controller should have these three things. One is data bus, another is address bus, as well as read and write control signals, as well as the control signals to disable its role as a peripheral and enable its role as a processor. So once DMA controller gets the permission from the microprocessor to take care of the buses and start transferring of the data directly in between the devices, that controller works as a master mode. And that master mode, there are two modes in which it used to work. It works as a slave mode whenever it is used to transfer the data, and it works as a master mode whenever it is working as a processor of actually transferring the data. So this process is called switching from the slave mode to the master mode. Now, for all practical applications, the DMA controller most of the time works as a processor which has the capability of copying the data at a very high speed from one location to the another location. Now let us go into the detail that how this 8237 DMA controller used to work. Now the 8237 DMA controller is programmable. Programmable means it can be programmed to operate in a certain fashion. You can write the instructions, you can write the information into the DMA controller for different types of the data transfers. This controller is also a 40-pin chip, and it has 4 independent channels, and each channel has the capacity to transfer. It is capable of transferring 64 kilobyte of the data at a time. Now the controller which is used, it must have 2 kinds of interfaces. One way of interfacing with the microprocessor unit, and another with the peripheral unit, meaning thereby this DMA controller works in between the microprocessor and the peripheral device. As I have already told you that DMA is going to play 2 roles in the given system. It is working as a slave mode, and in slave mode it is as good as the input output device for the microprocessor. That is called the slave mode. And if it is a data transfer processor to the peripherals, then it will be working in a master mode. Now many of the signals that are input in the input output mode become the output in the processor mode. That is going to be different. We will discuss it later on, that how it will be working as a slave mode and how it will be working as a master mode. It also needs some additional signal lines to communicate with the addresses of the 64 kilobyte, and these signals must be generated externally by using latches as well as the buffers. Of course, the 8237 is a little bit complex, but if we are able to discuss, we can discuss it into the 4 segments. One is DMA channel and interfacing. Second one is the DMA signals, then system interface, and then the DMA execution. So let us first discuss the DMA channels and the interfacing. This is the pin diagram of 8237 showing many signals. There are certain pins which are used as well as there are certain registers which are called the internal registers of 8237, which is shown in this particular figure. And it is also showing the interfacing of the microprocessor unit using the 328 decoder. Now, as I told you that this 8237 has 4 independent channels, and these 4 independent channels are known as or named as channel 0, channel 1, channel 2, and channel 3. Internally, 2 registers are associated with each channel. One is memory address register and another is the count register. Each channel has these 2 registers. That is why this is channel 0 memory address register and this is channel 0 count register. Channel 1 memory address register, channel 1 count register, channel 2, and then channel 3. Now, 2 registers which are used. One is used to load the starting address of the byte, which is required to be copied, and the second is used to load a count of the number of bytes to be copied. So meaning thereby the address is required for copying operation, as well as how many bytes has to be transferred. It is stored in the count register. So each channel contains both the registers. Which channel is used at a particular time, it depends upon the select signal and the address signal. So since we have 4 channels, so we have 8 such register. Individually, each channel will have 2 registers that can be accessed by the microprocessor unit. Now, address of these registers are determined by A3 to A0, as well as this chip select signal. The address, if it is 0000, it means if A3 to A0 is 0, then it means we are going to select the channel 0 memory, channel 0 register, channel 0 memory address register. And if it is 0001, it is going to select the count register. That is the channel 0 count. Similarly, all the remaining registers are selected in the sequential order. If it is 0010, it means it is a channel 1 memory address register. If it is 0011, it means 03 will be the address, that is channel 1 count register, and so on. And similarly, we have the result up to the 0F address. So this is the way how the addressing is of the individual registers are done from 00 to 0F. Now, this is the explanation that channel 0 to channel 3 each having 2 16-bit register, one for starting address of the byte to be copied and another is to load the bit count. The address is determined by A0 to A3 and the chip select signal, such as 000 selects channel 0 MAR, that is memory address register. 001 is going to select the next register, that is the count register, channel 0 count register. Last 8 registers are used to write the commands or read the status. We have channel registers. Besides that, we have some more registers: read, write, count, command register, write, request register, write, single mask register, write, mode register, write, clear byte pointer, read, write. So these are the certain other registers which is also accessed by the microprocessor by their own addresses, and especially they are meant for writing the commands or reading the status. This is how it is going to be selected. From A0 to A3 is going to select the individual channel register, and along with A4, A5, A6, it is going to select the different registers. So this is about the DMA channels and the interfacing. Now let us discuss about the DMA signals. Now we have many DMA signals which are associated with the DMA controller. Let us discuss one by one the individual lines of the pin diagram of 8237. VCC has not been showed. VCC is for the power supply. GND is not shown. GND is on the upper side. So GND is here, so it is for the ground purpose. Then we have another signal which is known as clock signal. Now this is the incoming signal of 8237, and this clock input is used to generate the timing signal which controls the 8237 operation. The next signal is the chip select signal, that is this one, and this chip select is an active low input which is used to enable the controller onto the data bus for the CPU communication. Then we have another signal which is known as reset. This is an active high input which is going to clear the command, status, request, or the temporary registers. And the first and the last flip-flop and the mode count register counter, the mask register is set to ignore the request. After a reset, the device will be in the 8237 will be in the ideal cycle. So whenever we are going to put a reset key, all these registers are going to reset or clear at, at one stage. Then we have a signal which is known as ready signal. This signal can be used to extend the memory read and write pulses from the 8237 to accommodate the slower memory or the slower input output devices. And these signals are connected with the ready signal of the, these signals are connected with the microprocessor unit. Then we have hold acknowledge signal. Hold acknowledge signal. This is active high hold acknowledge signal from which is coming from the microprocessor, and it's used to indicate that microprocessor has relinquished the control on the system buses. And HLDA is a synchronous input and must not be in transition. It has its specified time for that. And this signal, HLDA signal, is being generated only when the request signal is being sent from the controller. Now, what is the HRQ? HRQ is the hold request signal. This hold request signal, it is an output signal of 8237, which is used to request the control of the system bus. It is going to, this request signal is connected with the hold input of the microprocessor. So whenever any device is going to make the request through the channels, and this request is being accepted on the behalf of the different devices, this controller used to send the hold request signal to the microprocessor. And when there is a any request signal which is being received by the 8237 from the device, and its corresponding bit is clear, it is not masked, then 8237 is going to issue the high hold request signal. And the HLDA signal, once it has sent the request signal, once this HLDA signal is received, it is going to inform the controller while access to the system buses is permitted. It is now under the control of the controller. So that is the working of the HRQ. Now, what is DREQ to DREQ3? These are the DMA requests. And these requests are the request lines which are connected to the individual asynchronous channel requesting input used by the peripheral devices who want to avail the services of the 8237 controller. Then we have DB7 to DB0. This is the data bus. And this data bus lines are bidirectional, tri-state, connected to the system data bus of the microprocessor. And during the DMA cycle, whenever DMA starts its operation, the most significant 8-bit of the address are output onto the data bus to be strobed into an external latch, that is the ADSTB. Then we have other signals also: input output read, input output write. The function is very simple. If it is input output read, it means input output read is a bidirectional active low tri-state line. In the ideal cycle, it is an input control signal used by the CPU to read the control register. Similarly, input output line is also a bidirectional active low tri-state line. In the ideal state, it is again an input control signal used by the CPU to load the information into the 8237 controller. Then we have end of process signal. It is also a bidirectional. This end of process is an active low bidirectional signal, and information concerning to the completion of the DMA service is available at the bidirectional EOP pin. And 8237 is going to allow any external signal to terminate an active DMA service by pulling this EOP pin low. Then we have A0 to A3. This is the address line. These four least significant address lines are the bidirectional tri-state signal again. And in the ideal cycle, they are the input and are used by the 8237 to address the control register of the whether it has to be loaded or it has to be read. Similarly, we have four more lines, A4 to A7. This is also an address line. This is the four most significant address lines. And these and are three-state output. It work in a tri-state output and provides the 4-bit of the address. And these lines are enabled only during the DMA service. Otherwise, it remains disabled. Then we have DAC 0 to DAC 3. This is the DMA acknowledge. The DMA acknowledge is used to indicate the individual peripheral devices which are connected with the 8237. When one has granted a DMA cycle, the sense of these lines is programmable, as well as reset is going to be initialized them to active low. Meaning thereby, if any device wants to make a request, it will be sending the request through DREQ line, and accordingly, the acknowledge is being done with this line by the 8237. Then we have two more signal, AEN and ASTB. AEN stands for address enable and ASTB stands for address strobe. So AEN is an address enable, and this address enable enables the 8-bit latch, which is containing the upper 8 addresses onto the system bus. AEN can also be used to disable the other system bus drivers during the DMA data transfer. An address strobe is a active high signal which is used to control the latching of the upper address bytes. It will drive directly the strobe input of the external transparent octal latch, such as 82C2. Then we have memory read, memory write. Memory read signal is used for the memory reading purpose. This memory read signal is a low active signal, and it is a tri-state output. And it is used to access the data from the selected memory location during the DMA read operation or memory to memory transfer. Similarly, memory write signal is also an active low, and it is also tri-stated output, and it is used to write the data to the selected memory location during the DMA write or memory to memory data transfer. One signal is not mentioned, that is NC, that is no connect signal, and it is open and it should be tested for the continuity of the 8237. So this is all about the configuration of the lines of the 8237. And you have seen that these signals has been grouped into two parts. One group of the signal is on the left side, another group of the signal is on the right side. And the group of the signal which is on the left side, it is used for the interfacing with the microprocessor unit. And the second group that is on the right side, it is used for the communication with the peripheral devices. Some of these signals are bidirectional signal, and their functionality is determined that DMA is working in which mode. Meaning thereby, if DMA is working in input-output mode or it is working in a processor mode. The signals that are necessary to understand the DMA operations are very simple. That are DR request signal, DAC signal, then AEN and ASTB signal, memory read and memory write, the address lines, hold signal, HRQ, as well as the hold acknowledge signal. So we have discussed in a length that what is this signal and how this signal, what is the purpose of this signal. Then we have a system interface. Now DMA is used to transfer the data bytes between the input output and the system memory at a very high speed. Now it includes 8 data lines, 4 control signals, that is input output write, input output read, memory write, memory read, along with 8 address lines, that is from A0 to A7. However, since individual channel can work with the 64 kilobyte of the data transfer, so for 64 kilobyte of the data transfer, we are in need of the 16 lines. Therefore, we have to add additional 8 lines so that we are able to transfer the data from the individual channel. Now, whenever a transfer begins, the DMA is going to place the lower order byte on the address bus and the higher order bytes on the data bus. This has to be very clear about that lower bytes are placed on the address bus and higher order bytes are placed on the data bus. And it is going to assert AEN, that is address enable signal, as well as address strobe signal. Now, these two signal, AEN and ASTB, are used to latch the higher order byte from the data bus. Higher order bytes are available on the data bus. So these two signals are going to latch the higher order bytes from the data bus. Thus, it is going to place the 16-bit address on the system bus. Now, this is the way how it is going to do the, this is the interfacing with the interfacing of 8237 with the 8085 microprocessor. And in this 8085, in this interfacing, it is very clear that it is using two latches. One latch is here, that is latch number 1, and this is latch number 2, and both are same latch. 373 is the configuration of that particular latch. It has two: latch enable and output enable, latch enable and output enable. But how it works? Since two latches are shown here, latch number 1 and latch number 2, and these, let us discuss first about the first latch. Now, one latch, which is 373, which is number 1, it is used to latch the higher order bus, higher order address. It is used to latch the higher order address from the data bus. Now, through this, it is used to latch the higher order address, which is placed on the lower order address bus, lower order data bus, by using AEN as well as strobe signal. And this second latch, which is latch number 2, it is used to demultiplex the 8085 bus and generates the lower order address bus by using the ALE signal. This is connected with the ALE signal. So latch number 1 is using AEN and ASTB to latch the information which is available on the data bus to place it on the higher order bus. And this second one is used to latch with the help of the ALE signal, the content of lower order on the address bus. Now, this AEN signal is connected to the output enable signal of through the inverter. It means whenever it is high, it is going to become low, and output is going to enable. And this enable is going to latch the information and put the information at the A8 to A5. So this AEN signal is connected to output enable of the second latch with the high signal, which is going to disable the lower order address bus from the 8085. When the first latch is enabled, second latch will not work. When the second latch will be enabled, the first latch will not. So the first purpose is to latch the information of this address of the data bus, content of the data bus, and put it on the address bus, higher order address bus. And the second information, whatever is contained by the AD0 to AD7, is being latched at the A0 to A7. So this is how the system is being interfaced with the microprocessor.